Alright, back to recording and reading. Should I call the channel recording and reading? Anyways. Studio, don't send. We're still recording? I don't know. But whatever. Okay, consider the following problem that after each choice you receive a numerical reward chosen from a stationary probability distribution that depends on the action you selected. Oh yeah, we need to pull up the other thing. Oh, that was the last time. What if a human acts as a god and the system it's like tutoring. This is Haza tutoring. This is like tutoring. Alright. This is the original form of the this is the original form of the n-armed bandit problem, so named by analogy to a slot machine or one-armed bandit, except that it has n levers instead of one. Each action selection is like a play of one of the slot machine's levers, and the rewards are the payoffs for hitting the jackpot. Let's call it winning. Through repeated action selections, you are to maximize your winnings by concentrating your actions on the best levers. Another analogy is that of a doctor choosing between experimental treatments for a series of seriously ill patients. Each action selection is a treatment selection, and each reward is the survival or well-being of the patient. Today, the term n-armed bandit problem is sometimes used for generalization of the problem described above, but in this book we use it to refer just to this simple case. In our n-armed bandit problem, each action has an expected or mean reward given that that action is selected. Let us call this the value of that action. Each action has an expected or mean given, so split, and then we call that value of that action. We need to digest this, so digesting it, it's gonna be cuckoo berry. Are we still in A decide? Yeah, I think so. If you maintain estimates of the action values, then at any time step there is at least one action whose estimated value is greatest. We call this a greedy action. If you select a greedy action, we say that you are exploiting your current knowledge of the values. Why is it exploiting? If you're exploiting, it could be exploiting a few steps. Not only one step. If you select a greedy action, you say that, okay, if instead you select one of the non-greedy actions, then you say you're exploring, because this enables you to improve your estimate of the non-greedy actions value. Okay, yeah, makes sense. Exploitation is the right thing to do to maximize the expected reward on the one step. But exploration may produce the greater total reward in the long run. For example, suppose the greedy action value is known with certainty, while several other actions are estimated to be nearly as good but with substantial uncertainty. Good estimate, but it's still 10. Calculated. Alright, that was a good short break. While several other actions are estimated to be nearly as good but with substantial uncertainty, the uncertainty is such that at least one of these other actions probably is actually better than the greedy action, but you don't know which one. If you have many time steps ahead on which to make action selection, then it may be better to explore the non-greedy actions and discover which of them are better than the greedy actions. Reward is lower in the short run during exploration but higher in the long run because after we have, well, not certainly, but yes, most of the case. Yes, I don't know. Probably the interesting questions. After you have discovered better actions, you can explore them many times because it is not possible both to explore and to exploit with any single selection. One often refers to the conflict between exploitation and exploration. The other way. In any specific case, whether it is better to explore or exploit depends in a complex way or on the precise we have to read these again. Precise value of the estimates, uncertainties, and the number of remaining steps. There are many sophisticated methods for balancing exploration and exploitation for particular mathematical formulations of the unarmed bandit and related problems. However, most of these methods make strong assumptions about stationary and prior knowledge that are either violated or impossible to verify in applications and in the full reinforcement learning problem that we consider in subsequent chapters. Okay, technically and skill level, I need to get comfortable manipulating data. So, I'm going to do a video on how to what? The manipulation? Food is coming. Anyways, however, most of these methods make strong assumptions about stationary and prior knowledge that are either violated or impossible to verify in applications. And in the full reinforcement learning problem that we consider in subsequent chapters, the guarantees of optimality or bounded loss for those methods are of little comfort when the assumptions of in this book, we do not worry about balancing exploration and exploitation in a sophisticated way. We worry only about balancing them at all. In this chapter, we present several simpler balancing methods for the unarmed bandit problem and show that they work much better than methods that always exploit. And they need to balance games and the distinctive challenge that arises in reinforcement learning. The simplicity of the unarmed bandit problem enables. Well, I don't know. I wish they had given us a game or something. Just calling it in bandit problem. I don't know. Anyways, okay. Action value methods. We begin by looking more closely at some simple methods for estimating the values of action and for using the estimates to make action selection decisions. In this chapter, we denote the true actual value of action, A as Q of A, and the estimated value on the TF time step as Q. Recall that the true value of an action is the mean or reward received when that action is selected. Mean probably means here that over many samples get this reward. Okay. When the action was selected, in other words, if by the TF time step action A has been chosen and A times prior to T yielding rewards R1, R2 all the way to R and T parenthesis 8, then its value is estimated to be QT that all the rewards divided by number of times probably. If that is going to be defined instead as some default value such as being 0 as dangling by the law of large converges to actual true. Okay. Call this the sample average method. Alright, I just had an idea. What if moves add to 1 better to motor consoles? Okay, we are in search of ketchup. It's more important than reinforcement learning. He found it. If the moves values all add up to 1. we drop the values we decrement the values if we lose when one have set values. It's gonna be definitely a complex system. By looking down with a certainty of the action 3 and before actions. How do I yeah. Of course, this is just one way to estimate action values and not necessarily the best one. Nevertheless, for now, let us stay with this simple estimation method and return to the question of how the estimates might be used to select actions. The simplest action selection rule is to select the action or one of the actions with highest estimated action value. That is to select at step T. Yeah, I guess we should just randomly try it and see what works. Yeah, one of the greedy actions, A optimal for reach, and maximizes the value of that. This greedy action selection method can be written as argmax of A. Argmax denotes the value of A at which the expression that follows is maximized, which tie is broken. Okay. Greedy action selection always exploits current knowledge to maximize immediate reward. Spends no time at all sampling apparently inferior actions to see if they might really be better. A simple alternative is to behave greedily most of the time, but every once in a while, say with a small probability E, instead to select randomly from amongst all the actions with equal probability independently of the action value estimates. We call methods using this near greedy action selection rule E-greedy methods. An advantage of these methods is that in the limit, as the number of plays increases, every action will be sampled an infinite number of times. That as we go nt to infinity for all A, thus ensuring that all the estimated value converges to n. This of course implies that the probability of selecting the optimal action converges to greater than 1 that is to near certainty. They're just asymptotic guarantees, however, and say little about the practical effectiveness of the methods. To roughly assess the relative effectiveness of the greedy and epsilon greedy methods, we compared them numerically on a suite of test problems. This was a set of 2,000 randomly generated n-armed bandit tasks with n equal 10 for each bandit action values. QA goes 1 to 10. We're selected according to the normal Gaussian distribution with mean 0 and variance 1 on TF times step with a given bandit. The actual reward RT was the QAT for the bandit, where AT was the action selected, plus a normally distributed noise term that was mean 0 and variance 1 averaging over bandits. We can plot the performance and behavior of various methods as they improve with experience over 1,000 steps. We call this suite of test tasks the 10-armed test bed. Okay. We read this average performance of epsilon greedy action value methods on the 10-armed test bed. These data are averages over 2,000 tasks. All methods use sample averages as their action value estimates. The detail of the structure at the beginning of these curves depend on how actions are selected. When multiple actions have the same maximal action value. Here, such ties were broken randomly. An alternative that has a similar effect is to add a very small amount of randomness to each of the initial action values so that ties effectively never happen. Form their action value estimates using the simple average technique. The upper graph shows the increase in expected reward with experience. The greedy method improves slightly faster than the other methods at the very beginning, but then leveled off at a lower level. It achieves a reward per step of only about 1, compared with the best possible of about 1.55 on this test bed. The greedy method performs significantly worse. Performs significantly worse in the long run because it often gets stuck performing suboptimal actions. The lower graph shows that the greedy method found the optimal action in only approximately 1/3 of the tasks. In other 2/3, its initial samples of the optimal action were disappointing and never returned to it. The epsilon greedy methods eventually perform better because they continue to explore and to improve their chances of recognizing the optimal action. The epsilon equals 0.1 method explores more and usually finds the optimal action earlier, but never selects it more than 91% of the time. The epsilon 0.01 method improves more slowly but eventually performs better than the epsilon equals 0.1 method on both performance measures. It is also possible to reduce E over time to try to get the best of both high and low values. Sure. Okay, let's just read it. The advantage of epsilon greedy over greedy methods depends on the task. For example, suppose the reward variance had been larger, say 10 instead of 1. With noisy rewards, it takes more exploration to find the optimal action. And e-greedy methods should fare even better relative to the greedy method. On the other hand, if the reward ranks were 0, and then the greedy method would know the true value of each action after trying it once. In this case, the greedy method might actually perform best because it would soon find the optimal action and then never explore. But even in the deterministic case, there is a large advantage to exploring if we weaken some of the other assumptions. For example, suppose the bandit task was non-stationary. Okay, so we have like 5 levers. Start with one of them, and then we'll tell it to choose. It chooses this one, then it moves only like this or that. Not sure. As we'll see in the next few chapters, effective non-station is the case most commonly encountered in reinforcement learning. Even if the underlying task is stationary and deterministic, the learner faces a set of bandit-like decision tasks. Each of which changes over time due to the learning process itself. Reinforcement learning requires a balance between exploration and exploitation. Incremental implement. I'm such a genius. The action value methods, as we have discussed so far, all estimate actions values as simple averages of observed rewards. The obvious implementation is to maintain for each action a record of all the rewards that have followed the selection of that action. Then, when the estimate of the value of action A is needed at time t, it can be computed according to where here R1 are all the rewards received following all selections of action A prior to play T. The problem with this straightforward implementation is that its memory and computational requirements grow over time without bound. That is, each additional reward following a selection of action A requires more memory to store it, and results in more computation being required to determine Q A. And if you might suspect, this is not really necessary. It is easy to devise incremental update formulas for computing averages with a small constant computation required to process each new reward. For some action, the QK denote the estimate for its kth reward. That is the average of its first k minus rewards, given this average and a kth reward for the action RK. Then the average of all k rewards can be computed by 1 over k, 1 to k, that many rewards. Then it goes slow. Then this turns to, this is equal to this somehow. K minus that. I don't know what is happening here. I have no idea. Alright, we're gonna go up to 480, which holds even for k equal to 1, obtaining q2 equals to r1 for arbitrary, that's reward, for arbitrary q1. This implementation requires memory only for q, k, and k, only the small computation for each new reward. The update rule is of a form that occurs frequently throughout this book. The general form is new estimate is old estimate plus a step size target minus old estimate. The expression target minus is an error in the estimate. It is reduced by taking a step forward. Step toward the target. The target is presumed to indicate a desirable direction. Honestly, we can probably compute to the end of the gammon game. It probably takes a lot of time. Well, maybe not, because we will have two dice. Let's say you have 4 decisions. It's 4 to 10, 4 to 100, 4 to 100. It's 4 steps to 100. How much is that? It's gonna be 2 to the power of 200. And we need to parallelize this probably. How do we parallelize it? 2 to the 200 is a trillion times trillion. A trillion is 10 to the 12. So it's 5, it's 10 to the 60. 10 to the 60. Right. It's 10 to the 60. Then 10 to the 60, which is how much? What is that gonna be? No, it's way bigger than that. Oh yeah, I miscalculated that. We have 6 times 6. 36 different dice. It's 36 to the power. Well, it's constant. It's bigger. Okay, just say 10 to 60, which is not correct. Which is very not correct. Which is 2 to the 5. 2 to 500. Yeah, it is not correct. Full pointer. Okay, does 10 profit? Yeah. Definitely we're screwed. Definitely we're screwed. Okay. So we need to get a brute force then. That's for sure. So we need to be smart about it. But so if we can do, well, not necessarily. I feel like, yeah, let's do that. Let's do that. So on some time scale, one sec, 2 sec, let's go down, make a decision. And then when it came up, interrupt, get the value, then let the hyperparameters. That's interesting. Yeah, that seems about right. Okay. Note that the step size parameter used in the incremental method described above changes from time to time, from time step to time step, in processing the kth reward for action A. That method uses stepwise parameter of 1 over k. In this book, we denote the step size parameter by the symbol alpha, or more generally by ATA. Sometimes use the informal shorthand A equals 1 over k to refer to this case, leaving the dependence of k on the action implicit. Alright. The averaging methods discussed so far are appropriate in a stationary environment, but not if the bandit is changing over time. As noted earlier, we often encounter reinforcement learning problems that are effectively non-stationary. In such cases, it makes sense to weight recent rewards more heavily than long past ones. One of the most popular ways of doing this is to use a constant stepwise parameter. For example, the incremental update rule for updating an average qk of the k minus past rewards is modified to be that qk plus 1 equals qk plus alpha rk minus qk, where the step size parameter alpha equals to 0, including 1 is constant, results in qk plus 1. Being a weighted average of past rewards of the initial estimated Q1. That equals 1. Should I have explained this more? Not really. So just expanded it. For this, and from this we get qk equal to the one before that, and then we multiply it, and oh, interesting. Multiply to 1 minus a alpha equals times k minus 1 alpha r1 plus 1 minus alpha to k q1 1 minus alpha to q times q1. We call this a weighted average because the sum of the weights is 1 minus a k plus that. As you can check yourself, note that the weight alpha 1 minus a k minus I given to the reward r1 depends, or I depends on how many rewards they go. K minus I was optimistic initial values. Observe the quantity and the quantity 1 minus alpha is less than 1. Thus the weight given to r I decreases as the number of interventing towards rewards increases. In fact, the weight decays exponentially according to the exponent on 1 minus alpha. If 1 minus alpha equals 0, then all the weight goes on the very last reward. RK, because of the convention that accordingly, this is sometimes called an exponential recency weighted average. Sometimes it is convenient to vary the step size parameter from step to step. Let alpha k a denote the step size parameter used to process the reward received after the kth selection of action A. As we have noted, the choice alpha k parentheses alpha equals to 1 over k results in the sample average method, which is guaranteed to converge to the true action values by the law of large numbers. But of course, convergence is not guaranteed for all choices of the sequence. Alpha k a well-known result in stochastic approximation theory gives us the conditions required to assure convergence with probability 1. The first condition is required to guarantee that the steps are large enough to eventually overcome any initial conditions or random fluctuations. The second condition guarantees that eventually the steps become small enough to assure convergence. Note that both convergence conditions are met for the sample average case, but not for the case of constant step size parameter. Alpha k a equals alpha. In the latter case, the second condition is not met, indicating that the estimates never completely converge but continue to vary in response to the most recently received rewards, as we mentioned above. This is actually desirable in a non-stationary environment, and problems that are effectively non-stationary are the norm in reinforcement learning. In addition, sequences of step size parameters that meet the conditions often converge very slowly or need considerable tuning in order to obtain a satisfactory convergence rate. Although sequences of step size parameters that meet these convergence conditions are often used in theoretical work, they are seldom used in applications and empirical research. Alright, all the methods we have discussed so far are dependent to some extent on the initial action value estimates Q1A in the language of statistics. These methods are biased by their initial estimates for the sample average method. And the bias disappears once all actions have been selected at least once, but for methods with constant alpha, the bias is permanent, though decreasing over time as given by. In practice, this kind of bias is usually not a problem and can sometimes be very helpful. Why am I running out of energy? The downside is that the initial estimates become, in effect, a set of parameters that must be picked by the user, if only to set them all to zero. The upside is that they provide an easy way to supply some prior knowledge about what level of rewards can be expected. Initial action values can be used as a simple way of encouraging exploration. Suppose that instead of setting the initial action values to zero as we did in the 10-arm testbed, we set them all to +5. Recall that the QA in this problem are selected from a normal distribution with mean 0 and variance 1. An initial estimate of +5 is thus wildly optimistic, but this optimism encourages action value methods to explore. Whichever actions are initially selected, the reward is less than the starting estimates. The learner switches to other actions, being disappointing with the reward it is receiving. The result is that all actions are tried several times before the value estimates converge. The system does a fair amount of exploration, even if greedy actions are selected all the time. Okay. 2.2 shows the performance on the 10-arm bandit testbed of a greedy method using Q1A +5 for all action A for comparison. Also shown is an epsilon greedy method with Q1A equals 0. Initially, the optimistic method performs worse because it explodes more, but eventually it performs better because its exploration decreases with time. We call this technique for encouraging exploration optimistic initial values. We regard it as a simple trick that can be quite effective on stationary problems, but is far from being a generally useful approach to encouraging exploration. For example, it is not well suited to non-stationary problems because its drive for exploration is inherently temporary. If the task changes, creating a renewed need for exploration, this method cannot help. Indeed, any method that focuses on the initial state in any special way is unlikely to help with the general non-stationary case. The beginning of time occurs only once, and thus we should not focus on it too much. This criticism applies as well to the sample average methods, which also treat the beginning of time as a special event, averaging all subsequent rewards with equal weights. Nevertheless, all of these methods are very simple, and one of them or some simple combination of them is often adequate in practice. In the rest of the book, we make frequent use of several of these simple exploration techniques. Alright, we're gonna stop there. Gonna come back to it not tomorrow, probably Thursday. And we're gonna go over the math, definitely. And we're gonna continue with 5 to 10 other pages. So see you in the next one.